Swayam Prabha. Digital India. Educated India.
Welcome to this NPTEL lectures on cryogenic engineering. I am Milind Datre, professor in Department of Mechanical Engineering, IIT Bombay, and this is my first lecture on cryogenic engineering. Before I go into the details of what cryogenic engineering is all about, I just want to let you know what is cryogenics. Cryogenics is basically coming from the word cryo, which means very cold. From Greek language, this word has come, and genics means to produce. So, basically cryogenics means science and technology associated with generation of low temperature below 123 Kelvin. Now, why this 123 Kelvin? We can study about that later in the next lecture. However, what you have to understand is till 123 Kelvin, what you call is refrigeration, and if I want to achieve temperatures below 123 Kelvin, what we call is cryogenic engineering or cryogenics. This course aims at students who are interested to study the science and technology of low temperature. Basically, cryogenics is generation of low temperature. What is the science behind generation of this low temperature? What is the technology to achieve these low temperatures? This is all we are going to study in cryogenic engineering. The purpose of this course is to give introductory knowledge of cryogenic engineering. This is a course which normally we will aim at the PG level students or the final year undergraduate students having a good background of various subjects, and this course is meant for them. The course is both theoretical as well as mathematical. I am sure it will engross the students. This course will interest students who want to take career in cryogenic engineering. We know that cryogenic engineering is very widely used in space and atomic energy and things like that. And I am sure a lot of students will get motivated from this course in order to take their research career in cryogenic engineering. The prerequisites of this course are engineering mathematics, heat transfer, thermodynamics, refrigeration. Those who have done this course, which possibly can happen at the final year undergraduate learning or in the postgraduates or ME or MTech, I am sure those students will definitely appreciate this course. The points to remember while doing this course are: each lecture presentation ends with a self-assessment test based on the particular lecture. So, after each lecture or after a few lectures, we will have self-assessment test where the student can assess himself or herself. The best knowledge is gained when the students solve the self-assessment test very honestly and with proper understanding. So, we believe in that whatever assessment, self-assessment is to be done at the end of each lecture or after a few lectures, we feel that the student should take this test very seriously. At the end of the lecture, when he or she does this assessment, when they follow that a particular thing has been followed or not, will be visible to themselves when they do self-assessment. So, we expect that the students will do this very honestly. A greater insight into the subjects can be obtained by referring to the books specified. We are specifying some books for extra reading, for more general reading, for more special reading also, and we believe that these students will have hands on these books. They will go through these books and get some extra knowledge. Assignments are included wherever necessary in order to have clear understanding of concepts. We believe that whatever knowledge one gains out of this course, we have to do some assignments wherein a lot of fundamentals get cleared. A lot of mathematical problems will be there, some theory could be there. It will be clear only when you do these assignments very honestly. Before each assignment, an example tutorial problem will be solved with a detailed explanation. So, depending on the kind of assignment you want to solve, we will take a tutorial here, we will solve the problem step by step, we will see to it that one follows all the steps involved in those tutorials in this example or assignment problems, and after that we expect that the student will go through all the assignments honestly and come to an answer. Answers also will be given at the end of these lectures. The best knowledge is gained when the students solve the assignment problems honestly and with proper understanding of concept. I am sure you are clear with this. Now, there are various books available on cryogenic engineering. I am giving you some references here so that while doing this course, you may follow some extra reading with these books. The important book is by Randall Barron on cryogenic systems, available from Oxford University Press, and the last edition available is of 1985. This gives in summary on most of the topics I am going to cover in this course. In short, however, but then it will touch upon all the points. For some specialized reading, you will have to go to specialized books or journals. Then a book by Timmerhouse and Flynn on cryogenic process engineering by Plenum Press also is available. It's also a good reading for cryogenic engineering. Cryogenics also goes with vacuum, and therefore I have given here a book by Pipkov on fundamentals of vacuum engineering, where some fundamentals of vacuum which are necessary from cryogenic engineering perspective are given in this book. The next book is Thomas Flynn. The book is Cryogenic Engineering. The second edition is available as late as 2005. It is an interesting reading, and a lot of problems, assignments could be taken up from this particular book. Then we have got cryocoolers. I am going to talk about cryocoolers for about 6 or 7 lectures, and we have got books on cryocoolers part 1 and part 2 by Walker. The very famous books, in fact possibly these are the only 2 books on cryocoolers as per, and this also will give you some basic understandings on different cryocoolers, including pulse tube coolers, Stirling coolers. In addition to the books which I just talked about, we got various proceedings of the conferences that also gives a very interesting results related to contemporary research happening in the world, for which we propose the proceedings of advances in cryogenic engineering, the proceedings of International Cryocooler Conference, proceedings of ICEC or International Cryogenic Engineering Conference, or ICMC, which is International Cryogenics Materials Conference. In addition to these conference proceedings, what we have is Cryogenics Journal, and what we have in addition to this is Indian Journal of Cryogenics. Cryogenics Journal is published almost every month. It's a very prestigious journal. To get paper in this journal is also supposedly very prestigious. In addition to that, we have conferences alternate year in India, which are called National Symposiums on Cryogenics. And many times the papers which we present at this conference in the National Symposium are also becoming part of Indian Journal of Cryogenics, and that also can give you a perspective of what kind of research is being carried out in India or elsewhere. So all these books, in addition to the proceedings which I gave you and the journals, will form a very interesting and important reading as far as cryogenic engineering is considered. With this background, I will now talk about what I am going to teach in this course. So what is the syllabus for this course? The course syllabus is as follows. Now this course I am going to give under different topics, and there will be around 12 topics, and under each topic I will give you 1 or 2 or 5 or 7 kind of lectures depending on the scope of that particular topic. For example, the first topic or today's lecture is on Introduction to Cryogenics and its application. Today's lecture I am going to cover the topic number 1, which is Introduction to Cryogenics and its application. The next topic is Properties of Cryogenic Fluids. Now there are different cryogenic fluids, or they are called as cryogens also. For example, we have got liquid nitrogen, liquid helium, liquid hydrogen, liquid neon, liquid oxygen, etc. All these are normally called as cryogens, and they have got very specific properties associated with them. For example, liquid nitrogen has got its own properties, like what is its boiling point, what is its density, what is the latent heat of it. All these form a very important characteristics of liquid nitrogen. For example, liquid oxygen has a boiling point of 90 Kelvin. It has got its own density. Liquid helium has a boiling point of 4.2 Kelvin. So there are various important properties associated with these cryogens or cryogenic fluid. Now depending on the end use of this cryogenic fluid or the requirement of the cryogenic fluid, you will select a cryogen. If I want to get a temperature of 77 Kelvin, I will choose liquid nitrogen. If I want to use oxygen, then I will use liquid oxygen. If I want to go below very low temperature, in that case I will go for liquid helium, which gives me 4.2 Kelvin. So these properties are very important data in order to decide what is the cooling effect I am going to get from this particular cryogen. Depending on its density, depending on its latent heat, I have to select a particular cryogen, and therefore it is very important to study the properties of these cryogens or these cryogenic fluids. So this we will cover in the next topic, and under this topic possibly we will have 2 or 3 lectures covering different important cryogens. One of the most important parts for cryogenic engineering is the properties of material at cryogenic temperature. The materials are very important, and you cannot use all the materials in cryogenics. One can use only specific materials at very low temperature. It will be understood, I will show a demo sometime from now, how the material properties change at low temperature. So, there are different materials, for example, stainless steel, copper, carbon steel, aluminum, the properties of these materials change drastically at low temperature. This is a very important property. For example, specific heat capacity. What happens to its shrinkage? The material shrinks at very low temperature. What happens to this property? What happens to its conductivity? What happens to its ductility? These are very important properties, and this will study in detail in the topic called properties of materials at cryogenic temperature. Now, here I would like to conduct a small experiment to show you cryogen, that is liquid nitrogen, and I will show some material that are available with me right now, and you can have a look at this experiment. I am sure you will get a lot of knowledge after seeing this experiment. So, let us see the liquid nitrogen, because you must not have seen liquid nitrogen. So, what you see here in this video is a liquid nitrogen container, which is around 1 to 1.5 liter. So, here you can see that this is a specially made container which has got special insulation capacity, and what you can see also on this person is basically some safety devices, because you cannot touch liquid nitrogen directly. Also, you should not be able to see, you should not see the fumes which come as soon as liquid nitrogen is exposed to atmosphere. So, one has to be very careful about the safety that has to be taken into consideration while having a cryogenic experimentation. In fact, you will refer to my last lecture in this lectures, which basically addresses the point related to safety in cryogenics. Now, what we will do, this has around 1 liter of liquid nitrogen. I will put this liquid nitrogen into this container, which is a thermocol container, and let us then put some devices like some materials like rubber or potato and see what happens to the properties, the simple properties of these materials as soon as they are put or they are subjected to cryogenic condition. All right. So, let us see, while we transfer liquid nitrogen, have a look at how the liquid nitrogen looks and how it boils off immediately when it is put to the atmosphere. So, you can see the boil of fumes, and you can see the liquid nitrogen. It is like water actually, except that it starts boiling immediately, and the evaporation and the fumes are obviously there, they will always be there. Please note the safety devices again. So, here are two materials, one is a simple flexible rubber, you can see, all right, quite elastic in nature, and we will put this rubber in the liquid nitrogen. Also, we have got a potato, potato has got a lot of water, and as soon as we put this potato and the rubber, the properties will change. So, let us put these two materials for, let us say, 1 or 2 minutes, and you can see that suddenly the evaporation has increased. You can see how vigorous the boiling is, right. You can see the evaporation happening, you can see the fumes coming out of this, and you can see now how boiling is happening now. It has become still now, but you can still see the bubbles over there. It is getting settled down basically, and you can see some cracks having appeared over here right now only. Now, let us take out this rubber and let us see what happens to its properties. And you can see that it is not standing, it is standing like a very strong object, and you can see now it has actually become very, very hard. It is no more flexible, it can be broken into pieces, in fact, it can be crushed now. It has become as hard as knife also. And let us see potato, and potato, one can do the powdering of potato, it has become as hard as a stone, and one can actually make a powder out of this potato. So, you can see what has happened to these materials as soon as they were subjected to cooling, they were subjected to cryogenic conditions, and you can see these parts. In fact, now this rubber also can be powdered, the potato also can be powdered if they are crushed by some hard device, hard rock, and this is what happens, this is what shows what happens to these materials when they are subjected to very, very low temperature. This shows obviously that as soon as engineering materials also, when they are subjected to low temperature, the properties change. The fourth topic is gas liquefaction and refrigeration system. Now, liquid nitrogen, liquid oxygen or liquid helium, they become liquid only when you cool the gas. For example, when you cool nitrogen gas slowly from room temperature to its boiling point, then what you get is liquid nitrogen. But what is important to understand is how to reduce this gas temperature from 300 Kelvin to its boiling point. This is very important thing, for which you have to apply various techniques like compression and expansion of gas, the way we do in domestic refrigerator. In order to reach the lower and lower temperatures nearer to the boiling point of these gases, for example, 77 Kelvin for nitrogen, 4.2 Kelvin for helium and things like that, I have to devise a system whereby I reduce the temperature of gas from room temperature to the boiling point of these gases, and this is the most important thing. Not only that, it is important that how do I do that thing, but what is most important is how efficient I am doing, because in order to achieve a particular temperature, I can go by a process A or process B or process C. What is important for me to understand is which process is more efficient. That means my work input should be as minimum as possible in order to reach the boiling point of these particular gases. I need not compress the gas to a very high pressure, because the compressor work input is very high in those cases. This is what we will cover with different gas liquefaction cycle, and for a particular cryogen, then we will have to select that this particular cycle is the best. Similarly, like liquefaction, what we have is a refrigeration system also. These gases are ultimately utilized for giving cooling effect, or the cold or the refrigeration effect. For example, when I take the latent heat from these gases at their boiling points, what I get is a cooling effect at constant temperature. If I want to have an object which I want to cool it down to 77 Kelvin, 80 Kelvin, 50 Kelvin, 40 Kelvin, 4.2 Kelvin or 2 Kelvin, accordingly I will have to design the refrigeration system. For example, to have a superconducting magnet, what I need to have a refrigeration system or a cooling system. So, this topic number 4 is a very important topic and a very broad topic. I may take around 6 to 7 lectures in order to cover the gas liquefaction and refrigeration system at lower temperatures. Having done this, for industrial gases utilization, what is most important is gas separation. As you know, air is a mixture of various gases. If I want to get my hands on oxygen gas or nitrogen gas or neon, argon, helium, etc., ultimately I get it from air, which is a mixture of various gases. I have to ultimately liquefy air, which happens at 78 Kelvin around, and from where I will have to separate all these gases. Now, because of the mixture, this whole air as a mixture has got completely different properties, because different gases will liquefy at different temperatures, or they will condense at various temperature, and what is important is to understand the phase diagram of this mixture. So, the gas separation will depend on the boiling points of different gases in a mixture. For example, I got a mixture of nitrogen and oxygen or nitrogen and helium. I got two different boiling points, one for nitrogen, one for oxygen, or I got a boiling point for nitrogen and helium, which is 77 Kelvin and 4.2 Kelvin, or 90 Kelvin for oxygen and 77 Kelvin for nitrogen. In order to separate out this mixture effectively, in order to get pure gases from this, I have to devise a gas separation system. Basically, I have to understand how do I separate these gases, what should my work input be in these cases. This is normally done by fractional distillation, but then you have to devise or design a distillation column, and this is the most important part of it. So, gas separation along with gas liquefaction, or 4 and 5 topics, are very important to study in cryogenic engineering. The next topic is cryocoolers, and this also forms a very important topic of research. As I said earlier, there is the International Cryocooler Conference which happens only to bring out the research work that is being done all over the world at one place. For example, at IIT Bombay also we have been doing a lot of work on cryocoolers, and I will show now a simple cryocooler. What is a cryocooler? Cryocooler is just a refrigerator which produces very low temperature in a closed cycle manner. For example, I got different types of cryocooler, what is called as Stirling cooler, what is called as Gifford-McMahon cryocooler, what is called as pulse tube cryocooler. This is a cryocooler which is a Stirling type cryocooler developed at IIT Bombay. What you can see here is this is a cryocooler, and this part houses a compressor. In fact, it is called a linear compressor. It is a dry compressor, there is no lubrication in this. So, this is a compressor and this is expander. The way you see in domestic refrigerator, you got a compressor at the bottom of the refrigerator and you got expander which is actually a capillary tube. Then you got different heat exchangers also. Similarly, in this cryocooler, which is nothing but a refrigerator which produces very low temperature, this has also got a compressor. There houses a heat exchanger inside this, and there is an expander at the top of this thing. Now, I will show you what it is here. What you can see at the top is the cold finger. This is called as cold finger, and if I want to cool a certain object, I have to conductively couple that particular object to get connected with this cold finger. This cold finger is going to generate around 80 Kelvin temperature. For example, this cooler has been designed to produce around 0.5 watts at 80 Kelvin to cool some other object. So, in a closed cycle manner, there is a gas, which is helium in this case, is continuously compressed and expanded in a closed cycle manner in order to produce 80 Kelvin temperature at this point. So, this is nothing but a closed cycle cooler which works on Stirling cycle. That is why I call it Stirling cooler. So, it is called a Stirling cycle cooler producing around 0.5 watts at 80 Kelvin. In a very efficient design, if I want to carry out a very efficient design of this cryocooler, my power input to this compressor should be as minimum as possible, so that the coefficient of performance or the COP is very, very high. So, whole design analysis has to be carried out in order to understand or predict the performance of this cryocooler, and then one has to devise the dimensions of this cryocooler, fabricate it accordingly, and see the experimental results for this cryocoolers. In this way, we do Stirling cycle cryocoolers, GM cryocoolers, or Gifford-McMahon cryocoolers, or pulse tube cryocoolers, and things like that. The various types of cryocoolers which one can design. The next topic is cryogenic insulation. As you know, when I am going to talk about cryogenics, I am going to talk about very, very low temperature, and outside temperature of the ambient is 300 Kelvin, which is a very high temperature. So, the heat is going to rush from outside to inside, which is what we do not want. Otherwise, I want to cool a particular object, but because of the leakage of heat, ambient heat from outside, my cooling effect will be nullified. In fact, some of the cooling effect will be getting wasted as losses. So, in order to minimize that, what is more important or what is most important is the insulation. Now, insulation is a critical part of cryogenics, and depending on the low temperature I am talking about, for example, if I am talking about 80 Kelvin or if I am talking about very low temperature of 4.2 Kelvin, I have got different types of insulation, and these insulation are in different forms like perlite powder. It could be vacuum insulation. A vacuum is a very important part in cryogenics, and that is why my next topic is going to be vacuum. So, vacuum basically nullifies all the conduction and convection, or it removes all the air around the colder part. If I do not do that thing, the moisture in that air will get frozen down. Therefore, I have to remove all the air around the cold finger, and that is why vacuum insulation also is a very important part. I am going to show a very typical insulation here. What you can see is a very typical insulation, and here this is called as multi-layer insulation, and it has got highly reflecting surface like aluminum foil, aluminized mylar, like that. So, we can have a very highly polished surface, and we can have different layers of this. And each layer is separated by a non-conducting medium like nylon net. Okay. We can have some non-metallic stuff which is a nylon net or any other things which separate out, and this is what is called as multi-layer insulation. Now, this multi-layer insulation is wrapped around, for example, this is a cold finger. I will wrap this multi-layer insulation in a very typical manner, and what is most important is how many layers are there. So, one has to have 10 layers or 20 layers or 30 layers, that also one has to optimize depending on the temperature and heat in leak, and also the vacuum around. So, multi-layer insulation works only when there is a vacuum around it, making effectively the thermal conductivity across this direction from outside to inside as minimum as possible. It could be 0.0001 conductivity could be of this order, all right. So, the conductivity gets drastically reduced when multi-layer insulation is there. So, if I want to reach very low temperature, I have to use multi-layer insulation in presence of vacuum in those cases, all right. So, insulation is a very important part in cryogenic engineering. This has to be taken care of effectively depending on the end temperatures or the low temperatures we are going to be talking about, 77 Kelvin or 4.2 Kelvin or 25 Kelvin. This will decide what insulation I am going to use. As I just said, vacuum technology is a very important part, and vacuum is a very integral part of cryogenics. So, what is this vacuum? What are different types of vacuum? How do you get these vacuums? What are different vacuum pumps is also have to be studied in cryogenics. So, this part also will be covered in cryogenics while learning this topic. The next important part is instrumentation in cryogenics. You can understand instrumentation at room temperature and instrumentation at very low temperature has to be different. For example, if I want to carry out temperature measurement, pressure measurement, or I got different cryogens kept in a cryostat, and therefore I should know how much liquid nitrogen is left there. So, what I call is a level measurement. I should know that it was 100 liters today, tomorrow it could be 90 liters, day after it could be 75 liters, depending on the usage and depending on the losses. So, I have to measure in cryogenics the temperature, pressure, level, mass flow rates, and whatever technique I devise at room temperature are not applicable at low temperature. One has to follow a different technique because the properties or the calibration is completely different at low temperature. For example, just for today's lecture, if I talk about measurement of temperature at very low temperature, for example, at 4.2 Kelvin or 10 Kelvin, what I use is something called as silicon diode. If I want to show you, this is a silicon diode. This is a very small piece and this has been calibrated to measure temperatures up to 1 Kelvin. This is a very costly piece. If you get it calibrated, it is a very costly piece still. This is a diode. At lower and lower temperature, the voltage or the resistance starts increasing and this is calibrated in terms of temperature at lower and lower temperature. In addition to this, what I have also is a PT100. This is called platinum 100, and what you can see from here is PT100 can measure the temperature up to 30 to 40 Kelvin. Let us say 50 Kelvin is better. From room temperature to 50 Kelvin, I can measure the temperature. When I say PT100, it has got 100 ohms resistance at 0 degree centigrade. So, these are the two things I can show. I can measure the temperature up to 50 Kelvin using PT100 and I can measure temperature up to 1 Kelvin using silicon diode. So, these two are very important temperature measuring sensors which are generally used in cryogenics. Alright. So, one has to understand how do that measure temperature, what is the philosophy behind the temperature measurement in these cases, what are corresponding errors, how do I employ these things in the actual instrumentation and things like that are very important aspects of cryogenic engineering instrumentation. And finally, what is most important in cryogenics is safety. One has to observe certain norms, one has to use certain gloves, we have to use goggles and things like that. And why do you have to do all these things? Because you are working at very low temperature. If there is a small accident, if the nitrogen in the atmosphere increases or oxygen level drops down, you can suffer from something called as asphyxiation, and I will talk about all these things later in the chapter, very important chapter or topic on safety in cryogenics. These are different topics which I am going to cover in this syllabus. I will take several lectures under each topic in order to cover these. Now, after understanding what is covered in this, what I want to bring your attention to is what are different applications of cryogenics. Now, cryogenics has got different application in space, in mechanical engineering, in medicine, in superconductivity and things like that. I am just going to show certain examples. I may not go into the details of each of those applications because each of those applications are chapter by themselves. What I am going to go is to go through this slide. You might read that with me and I will just take you through this slide so that you get a glimpse of what those applications are of cryogenic engineering in these different special topics. For example, space. Under space, I got cryogenics in rocket propulsion, cooling of infrared sensors or space simulation. These are very important aspects of cryogenics used in space. Now, what are they? Cryogenics engines are powered by cryogenic propellants. You know, different propellants are there, but if I use cryogenic propellant, for example, liquid hydrogen can be used as a fuel to propel the rocket. Most of you have heard about cryogenic engine, and cryogenic engine uses liquid hydrogen as a fuel. It also uses liquid oxygen as an oxidizer. So, these two are important components. Liquid hydrogen is liquid at 20 Kelvin, liquid oxygen is liquid at 90 Kelvin. These two form the fuel for cryogenic engine and therefore, it can work as cryogenic propellant, and these are very important. The next is cooling of infrared detectors or telescopes or cold probes are some of the major applications of cryogenics. I have to use infrared detector in space because when I am taking night surveillance, when I am taking picture, I got infrared detectors. Now, in order to get a good signal to noise ratio, that means in order to get a good image, I have to have detector at very low temperature. In fact, lower the temperature of this detector is better the picture or less is the noise, and therefore, infrared detectors have to be kept cool at 80 Kelvin or less than that. As I said, lower the temperature, better it is. Similarly, I got lot of electronic circuits in space. If I cool these circuits down, for example, amplifiers or any electronics which gets heated over a period of time, if I got cold probes, I can keep it very cold and therefore, the noise level will be minimum in this case. These form a very important application of cryogenics in space. In order to do that, what I do is normally develop miniature cryocooler which goes in space, and the cold finger I just showed you earlier, Stirling cooler for example, is very widely used to cool the infrared detector in space. And what is important therefore is to design a miniature version of Stirling coolers, less weight and less volume, which are very important things for space. Space simulation chambers are a realistic environment for spacecraft. The cold space is simulated at cryogenic temperature by use of LN2 or liquid nitrogen. So, the space simulation chamber basically simulates space. What is space? Space has got very less temperature of around 4 Kelvin and very less pressure, that means vacuum. All these things have to be simulated on the ground. If any part you want to take in space, it has to first get space qualified, which will what will happen in space simulation chamber. It's a small test which is done on the ground, which simulates condition in a space, wherein the low temperatures are generated by different cryogenics like liquid nitrogen, liquid oxygen, etc. At the same time, different levels of vacuum are required in space, and what we do for this? We use cryo pumps or turbomolecular pumps. In this way, we can achieve lower and lower vacuums to simulate condition like what it is in space. All right. These are very important applications of cryogenics in space. If I move away from space, I go to mechanical engineering now, wherein the applications of cryogenic engineering are in magnetic separation, heat treatment of different materials, or recycling of certain materials. There are various applications, but I will touch upon only 3 of these aspects in this particular lecture. What is magnetic separation? The magnetic separation technique is used in variety of applications like enhancing the brightness of kaolin, this is the clay, improving the quality of ultra high purity quartz, etc. What we use is a superconducting magnet, ensures proper separation. So, what I am doing is basically when I get this kaolin clay from different ores or mines on the eastern part of India, for example, it gets associated with lot of metals, and in order to separate these materials or metals like silicates, etc., what I use, I pass the whole thing through some magnet, and these materials or metals will get attracted towards this magnet. After that, the kaolin will be free of these metals. However, in order to separate out these materials from the kaolin clay, what I need is a very high magnetic fields, and these high magnetic fields can be achieved only by superconducting magnets and not by electromagnets. If I were to use electromagnets, then my current passing through these wires will be very high, and therefore losses will be very high. So, what I have to use for this is basically superconducting magnet. This is very widely used techniques. Superconducting magnets are meant for magnetic separation, are very big magnets through which the kaolin passes and it comes out without these metals at the other end. Similarly, cryogenic heat treatment is given to a lot of metals. As you go on cooling the object, for example, what we do in tempering and annealing is you first go to a very high temperature and start cooling the object, and we stopped at ambient temperature. If I don't stop at ambient temperature and go below to cryogenic temperatures, there is something called as written austenite, which will get converted to martensite, and which is what we want. The written austenite is very brittle sometimes, and therefore I would like to have complete conversion of this austenite to martensite, and therefore cryogenic treatment of very special metals is carried out, and you get a better metal at the end of the heat treatment. What do you get at the end is the lives of the tools, die castings, their dies, forgings, jigs and fixtures, etc. increase when subjected to cryogenic heat treatment. This is very important. The life of guitar string increases by 4 to 5 times with no need for tuning. So, here you can see that the life increase is there because of cryogenic heat treatment carried out to liquid nitrogen temperatures. Cryogenic recycling turns the scrap into raw materials by subjecting it to cryogenic temperatures. There are certain materials like rubber or plastic which we want to scrap, and it's not very easy to scrap these things. So what you do, you expose this material to very low temperature. You put them in a, let's say, liquid nitrogen bath. As soon as you do that thing, as we saw in the experiment, this material become very hard. It becomes very rock hard, and then one can use some kind of press in order to crush. The whole scrap can be crushed like a metal in those cases, and it will ultimately get converted to powder. It is very easy to scrap in the form of powder. So if you have got a huge raw material, for example PVC, rubbers and plastics, etc., you can give a cryogenic treatment to those things. You can give a cryogenic recycling treatment to those, subject it to low temperature and crush it to powders. Various designs are available, various systems are being followed all over the world. This forms a very important applications of cryogenics in mechanical engineering. Moving away from mechanical engineering to medicine, this is, again, is a very important aspect of cryogenic engineering usage in medicine. One can use cryogenics in cryosurgery, cell preservation or food preservation. Preservation industry is huge as far as cryogenics is concerned. From the medical point of view, I will show you what its usages are. Cryosurgery is a novel technique in which the harmful tissues are destroyed by freezing them to cryogenic treatment. This surgery is carried out for various aspects. For example, dermatologists use this surgery just to remove unwanted moles or something like that on your body. Some treatment is given on your skin by doing a small surgery at very low temperature. Why? Cryosurgery has shorter hospital stay, less blood loss and small recovery time. This is a very important aspect. One can go in the morning and come back in the evening. That kind of cryosurgery are also possible, which is done at very low temperature. It is generally used in patients with localized prostate or kidney cancer, skin disorders, retinal problems, etc. This list is actually increasing with time. However, the data is keep coming. There are certain heart elements also that could be treated using cryogenic techniques. When it comes to preservation, the preserving food at low temperature is a well-known technique. This is what we do in a domestic refrigerator. Cooling of seafood, meat, milk products, long time preservation is achieved using liquid nitrogen. Liquid nitrogen is very widely used for transporting seafood or meat or milk from a port A to port B. One can keep everything preserved in an original form, frozen at cryogenic temperature. And therefore, this is a very important technique. A very massive work is being carried out as far as preservation of food using cryogenic technique is considered. Systems are developed to preserve blood cells. This is again a usage in medicine. You can preserve blood cells, plasma cells, human organ and animal organs at cryogenic temperature. So, the preservation using liquid nitrogen bath to preserve blood cells, plasma cells, human cells, stem cells also is the latest addition to this list. This all thing is done at cryogenic temperature. Coming next from here to the gas industry. As you know, gas industry is basically the gases. The industrial gases is a very sought after. For example, oxygen, nitrogen are used. Oxygen is used in medical hospitals, and therefore the gas industry is a very big industry, and the gas industry therefore uses cryogenic techniques for liquefaction, separation and storage. The very important aspect of cryogenics, very important usage of cryogenic. The transportation of gases across the world is done in liquid state. One need not do the transportation of the gases in the gaseous form, because if you want to do the transport of gases in gaseous form, the gases are compressed at a very high pressure, which is sometimes unsafe, which is not accepted sometimes. So, what you do, you convert those gases to liquid by lowering the temperature, by liquefying those gases using cryogenic techniques. And this is done by storing the liquid at cryogenic temperature. If I get liquid of those particular gases, I can store those liquids at cryogenic temperature, and in this way I can do transportation much easily as compared to those in case of gases. The use of inert gases in the welding industry has initiated higher demand for gas production in the recent past. Nitrogen, oxygen, all these things are very widely used in the industry, and therefore these gases require cryogenic techniques to liquefy those gases and transport those gases and store those gases. and this is a very high demand of gases for cryogenic gases like nitrogen, oxygen, neon, argon, etc. Cryogenics like LOX, which is liquid oxygen, LH2, which is liquid hydrogen, are used in rocket propulsion as we have just seen earlier, while liquid hydrogen is also being considered for automobile. You may know that a lot of research is being carried out to use hydrogen as a fuel in an automobile. In fact, a car is already ready which uses liquid hydrogen like as a fuel, like what we do in using petrol or diesel. So, here all these gases, all these liquefied gases play a very important role as they are needed to be consumed in these forms. Liquid nitrogen is used as pre-coolant in most of the cryogenic system. Whenever I want to do cooling, I got liquid nitrogen as a very cost effective way which will reduce the temperature from room temperature to 77 Kelvin. As you know, nitrogen is available in air, so nitrogen is freely available, one can say. It's a very cost effective solution to reach 77 Kelvin. And in most of the liquefaction cycles, nitrogen is used as a pre-coolant in order to reduce the temperature from room temperature to 77 Kelvin. The steel industry is a very important consumer of these gases, and you can find a lot of liquid oxygen plants on the campus where the steel industry is housed. So, in steel industry, oxygen is used in the production of steel. Basic oxygen furnace uses oxygen instead of air. So, you will find at a lot of places liquid oxygen becomes a very important requirement for the steel industry. Nitrogen and argon are primarily used to provide an inert atmosphere in chemical, metallurgical and welding industries. So, these gases being inert gases, they are stored in the form of liquid nitrogen or liquid argon instead of storing in the forms of very highly compressed cylinders. It creates problem as far as safety considerations are taken in. The next biggest application is superconductivity. Superconductivity has got various uses in NMR, MRI, magnetically levitated trains, transformers and generators. This is a very important aspect of cryogenics. In fact, superconductivity came into existence because of cryogenics, and it has got important usage in various aspects, important being the NMR or the nuclear magnetic resonance and MRI, which is a magnetic resonance imaging which you find in hospitals. So, one of the major important usages of superconducting magnets is a NMR, which is a nuclear magnetic resonance. It is used by the various pharmaceutical industry to study the molecular structure. If I want to devise a new drug against any particular disease, I have to do NMR in order to understand the molecular structure in 3 dimensions. What I do for that is an NMR, and NMR has superconducting magnets here. What you can see here is a superconducting magnet, and in this superconducting magnet what I have got is a small sample of a chemical of which I want to study certain properties. In order that this magnet becomes superconducting, this magnet could be kept dipped in liquid helium and one can have liquid nitrogen outside. So, if you have seen any NMR facility, you can always see that NMR facility will continuously require liquid nitrogen or liquid helium in order to keep these superconducting magnets in a superconducting state all the time, because slowly the liquid helium level will start going down and slowly liquid helium state also will start going down, and therefore, we need cryogens to be supplied all the time. The magnetic field which is generated by these is around 10 to 25 Tesla. Higher the magnetic field, better is the structure that is visible to us, and therefore, the need of superconducting magnet in this case. Similar to that, what you have got is the MRI, which is a magnetic resonance imaging, and this is again used for body scanning. As you can see the picture over here, this is a magnet, and then we have got different coils which take a signal of this person sitting over here. MRI is meant for basically body scan, while NMR is meant for chemicals. In order that these magnets are kept in superconducting state all the time, they are dipped in liquid helium here, and then you can find different shields outside. Sometimes this liquid helium will be surrounded by liquid nitrogen, or we can use a cryo cooler which can produce shields of 40 to 50 Kelvin or 20 Kelvin outside of this liquid helium, so that the boil off is minimum in this case. This is a very important applications of cryocoolers in MRI field. In fact, MRI field has really initiated the research better and better efficient cryocoolers and functioning, and also minimum vibrations in these cases. And this is the way MRI will be done. The superconducting magnets for both NMR and MRI machines are cooled with liquid helium, and nowadays with cryocoolers also. Next application is magnetically levitated trains, which run on the principle of magnetic levitation. The train gets levitated from the guideway by using electromagnetic forces between superconducting magnets in the vehicle and coils on the ground. So, this is the very important applications of superconducting magnet, which uses cryogenics to go into superconducting region. This particular thing results in no contact motion and therefore no friction. So, imagine a train running with a speed of 600 km per hour, having no contacts with the rails and therefore no friction, therefore no wear and tear, therefore no servicing requirements. It's a great application of cryogenics. Similar to this, the next applications are superconducting transformers, motors and generators. Wherever there are windings involved, wherever there are I square R losses are there, if we could put those windings in liquid nitrogen or liquid helium, the I square R losses are going to be absolute minimum or 0. There are different ways in which these superconducting wires could be achieved. Superconductivity of these wires could be achieved by various cryogenic arrangements, cryogenic systems that we have to study. However, because of superconducting transformers, generators and motors, cryogenics is reaching to a commercial state now. And lastly, I would say the recent experiments which most of you have seen at CERN, and now the biggest project on earth is ITER, are the important applications of cryogenics in high energy physics. CERN is an European organization for nuclear research which was founded in 1954. It consists of a 27 kilometer accelerator ring with 4 detectors. Possibly most of you have heard recently the results what you got at CERN. It houses superconducting magnet ring. All the magnet system which is there in this 27 kilometer accelerator, it has got superconducting magnets, and all these magnets are kept at 1.9 Kelvin using liquid helium. So, you can imagine an immensely application of cryogenics, a biggest application of cryogenics at CERN. In fact, a lot of research in cryogenics originated from CERN because of these big applications. A liquid nitrogen layer of 77 Kelvin is used as shielding for liquid helium. It is an experiment, most of you know, it's an experiment seeking answers to Big Bang theory and collision of atomic particles. Basically, it studies the origin of universe in this way. The next big application after CERN has been ITER, International Thermonuclear Experimental Reactor. This is an engineering project for nuclear fusion reactor. This is a very important project which is, I think, the biggest project right now on the earth. The superconducting magnets are maintained at low temperature by gaseous helium. These experiments are carried out to enable mankind to generate energy for future. So, ITER experiments, if you go on net, you can get lot of information on CERN and ITER experiments, and these experiments we seek that this will possibly solve our problems for energy in future. So, I have given you various applications of cryogenics, and just in summary, I would like to give space application, application of cryogenics in medicine, application of cryogenics in mechanical engineering, high energy physics, then gas industry and superconductivity. This is in short all the applications of cryogenics in various fields which are very important. In addition to that, what we have is a cryobiology, in biotechnology, in cryophysics and things like that, where they got fantastic applications of cryogenics in this field also. I will stop here. Thank you very much, and in the next lectures we will cover different aspects of cryogenic engineering. Thank you.